Okay, I want to talk identities for a little while here. So let's move on to the next page. So first of all, with identities, let's make an analogy. Identities is just a fancy way of saying this is an equality. It's an equality that I know about. So if I give you a problem like this, I could say simplify, and we'll do something really simple, but I could say simplify the following. So x plus 2 minus x plus 1. Okay, now you know that, hey, I really don't even need those parentheses at the front, and so I could treat that as just x plus 2, not x squared, sorry, x plus 2. Now this one I do need to distribute, so those parentheses do matter. And so if I do that, I get minus x minus 1. And if I work that out some more, actually I'll fill my space here. Well, the x minus the x, well, those cancel each other out, and then 2 minus 1, well, that's just 1. So actually, at the end of the day, I have simplified, but furthermore, though this probably wouldn't pop up a lot, I could say, hey, I have the following identity. I found a fun way to rewrite the number 1. In other words, anytime I see this on the left, I could just rewrite it with the number 1. Now that'd be kind of silly, I think. The thing on the left, it's probably not going to pop up a lot. We're probably not going to see it a lot. In fact, it would just in basic algebra, I think you give me something in algebra, typically I think I'm going to just do the algebra and use my properties and simplify, right? I'm not going to remember this random equality here that works. Though this is always true. This is just using algebra. We know this is always true all the time, right? Another example, maybe slightly harder, is what if I gave you this and I said simplify? So let's see here. X squared plus x over x squared minus 9. Excuse me, x squared minus 9x plus, nope, minus, excuse me, minus 10 over x minus 9. Now I see some things right away. So if I was to just do some algebra, I could say, hey, you know what? Both the top and the bottom on the left here, they both have x's. I'm going to factor some x's out, right? So I have x times x plus 1. I have x times x minus 9. Oh, that's going to work out nice. I still have this part. And so let's see here, these cancel. All right. And oh, now I have a common denominator. So now that I have a common denominator, I can put these together. So with a common denominator, it'll be x minus 9 with the common denominator. And then now be careful. This will be, let's see here, get my pointer. So x plus 1 minus 10. So x plus 1 minus 10. And then, oh, well, 1 minus 10, though. That's just negative 9. Oh, geez. So x minus 9 over x minus 9, that always cancels, and that is equal to 1. Oh. So, in other words, I could say anytime I see this, oops, minus, I know that it's equal to 1. Right? So that left side, if I was to ever see that left side there, I know that I could technically just swap it out and replace it with 1. And there you go. Now again, that thing on the left in blue, it's really random. It would be kind of hard to remember. It's probably not going to pop up a lot. And in fact, if you handed it to me, it'd probably be easier for me just to do the algebra to simplify real quick rather than try to remember this equality, right? So that's what identities are. They're like this. You sort of have some algebra property. You find out, hey, I can simplify it into this other thing. All right, and for sure, using 1 on the right-hand side would be a lot easier to deal with whatever's on the left-hand side here in these two examples, right? If I could just swap it out and replace it with 1, my life would be so much easier, okay? All right, so now, like I said, these are just regular algebra. These are really random, hard to remember. Now, with trig, that's not true, though. With trig, we have identities, and these things come up a lot. Okay, so certain algebraic expressions with trig in them come up a lot, and so seeing that and to be able to swap things out is really good because, you know, if you look at your graphs, remember trig graphs are actually like sines and cosines. They're really the same graph, they're just phase shifted, right? So sometimes, you know, if those phase shifts line up, you could really swap one with the other, etc. And you know, so all sorts of fun things. We have, you know, things like 1 over sine, right? Well, that's just equal to what? Cosecant, right? We have a special name for that, and that's mostly just to say, hey, 1 over sine, I have something in the denominator. We don't like things in the denominator typically, and so we rewrite it in a simpler way, keep cosecant, right? But they mean the same thing, but swapping one for the other can be helpful, right? Plus just all sorts of other fun things, okay? And so it's about taking algebraic expressions that have trig in them and replacing them with things that are sometimes simpler, right? And the whole reason is to make my equations simpler or to swap things in, because then when I combine it with something else in the equation, perhaps, things can cancel and actually simplify even further yet, okay? And this happens a lot with trig, and it's super helpful. All right. So some tips, though, as we go through this. First of all, I think it's always a good tip if you see a trig identity and we say, hey, prove this is an identity, well, you would what? You would change everything to sine and cosine. That's always a really good tip, a really good step to follow. Look for your sine squareds and cosine squareds, because, you know, the most popular and powerful identity is what? Sine squared plus cosine squared equals 1, right? And so if we see sine squareds and cosine squareds, we could use this. Remember, alternate forms of this is if we move the cosine over, then we get this. Or if we would have moved the sine over, we get this, right? Alternatively, then sine squared x minus 1 equals a negative cosine squared. I mean, so I could go for days, but if you see sines and cosines, you have all sorts of fun things, right? So that's a really popular one. If we see those, we want to use that kind of identity, right? And then the other big thing is whenever you have an identity, probably the biggest mistake I see, you're trying to prove this equality. You don't know it's equal. So we're not solving an algebra equation. Think of it as what I did back on this page. We're simplifying. Okay? And you're trying to simplify to show that, hey, when I simplify, I get the thing on the other side, and therefore, I know these two things are equal. Sort of like what I did here, right? I didn't just go, hey, this is equal to 1. I took this, I simplified it down with my algebra skills, and then I saw, oh yeah, it is equal to 1. In other words, proving that this is true, or in other words, that this is an identity, right? Same thing here. I took this expression on the left side, and I just did algebra, oh, and I got to 1. In other words, proving this identity is true, okay? So that's the other thing here is you should only pick one side, manipulate it with algebra, and then show you can get to the other side. Okay? Do not use both sides because you do not know they're equal. You're trying to prove they're equal. Okay, I cannot stress that enough. Now, the funny thing though is when you do pick one side, it's actually usually easier to start with the more complicated side. And the reason why is the more complicated side has more expressions in it, which means then you have more things to work with and you don't have to maybe guess as much about what to do. As where something with less things, it's maybe not as obvious or as clear what to do, and you kind of have to, guess a little more about what do I do with this. So actually you want to use the complicated side, and that tends to work out a lot better. All right, so let's look at some examples. So I'm actually going to solve this, I think 2 different ways here. Actually, I think I got 3 different ways to solve this one. All right, let's do it. So first of all, I think the left-hand side is easier than the right-hand side. So I could just do some plain algebra on the left-hand side. So if I did some plain algebra, again, think of this as like a question mark. I don't know that's true. I'm trying to prove it's true. So I'm going to take the left side. All right, let's take this one. And let's work with that one, and let's show it's true. Okay? So these are just 2 binomials, and so I'm going to just distribute these out. And so I'm going to take sine times this one, sine times this one, and then the negative cosine times that, negative cosine times that. And so we'll just distribute this thing out, see what we get. I'm going to do that in black. So sine theta times sine theta. By the way, theta, x's, y's. Theta is just a variable. It doesn't matter if I'm using thetas or x's. All right. We just like to use theta a lot in our trig, right? So sine times sine. Well, that's sine squared. Remember, having the 2 here, that's where we put our squares. That is equivalent. If I write it up here, maybe that is equivalent to this. Okay, we just put the square down there because it's cleaner, it's more convenient. All right, it's just a notation thing, and it's unique to trig, and it's just you kind of got to get over it, right? It's how we do things. It's sort of like with natural log, right? Instead of writing the natural log or log base e of x, we say, hey, you know what? We're just going to do this notation thing to make it simpler and easier, right? And so we do ln, right? But it really means log base e. So again, it's just a notation thing to make our life easier. So get used to that if you haven't already. Sine theta times cosine theta. Okay, well that's just sine theta times cosine theta, right? All right, now negative cosine theta times sine theta. Well, that's just minus cosine theta times sine theta. Oh, that's good. I see something already. And then last but not least, minus cosine. Don't forget the minus there. Minus cosine theta times cosine theta. So that's going to give me a minus cosine theta. Or excuse me, cosine squared theta. All right, so what do I see? sine, cosine, sine, cosine. The order's swapped, but again, multiplication order doesn't matter. And so those two things actually cancel. Goodbye. And then I get what? Sine squared theta minus cosine squared theta. Oh, that's nice. Still doesn't look like the right hand side. It's close. Now, I do notice that what? I need to end with a cosine squared. So I should probably leave that alone because that's already getting me close. Notice there's no sine squared over here. So in other words, I need to get rid of this somehow. Oh, well that's where, like on the last page, right? Sine squared, if I use my identity, sine squared theta plus cosine squared theta equals 1. I know that if I pull that pull that cosine over, I get this. Aha. So I'm going to use this. So sine squared I could replace with 1 minus cosine squared. I have a minus cosine squared. Oh, there we go. By the way, I guess I should say these are I'm taking that green chunk. It's equal to this, equal to this, equal to this. And aha, well, I have a minus cosine squared, a minus cosine squared, so that's two of them. All right, nice. And that's exactly what I want. Ta-da! So now I've proven the identity. I've shown that the left-hand side, if I manipulate it or simplify it, if you will, in some ways, I can get the right-hand side. So in other words, I've shown that that equality is true, or in other words, I've proven that identity. Okay? So if I ever see the left-hand side, I could swap it out with what's over there on the right, or vice versa. If I have the right-hand side, I could swap it out and replace it with what's on the left. All right. Now, right now, it maybe is not obvious why that's helpful, but I'm here to tell you that in calculus, swapping things out like this, if you have identities, are really, really helpful. And you can swap something out, and all of a sudden you see something else that cancels, and then you cancel, and then you see something else, and then you whittle it down, and then you just get this much, much, much easier expression than what you started with. And it can make life really, really easy, or much easier. All right. And so that's sort of the idea behind this. This can often happen with trig. All right. So that was one way. Let's look at it another way. Let's see here. I could work, let's see here, am I going to work with the left-hand side or the right-hand side? I'm going to work with the right-hand side. So let's do this side this time. I'm going to use some algebra. I'm going to work with the right-hand side, try to get to the left-hand side somehow. Now, I would say this is the less complicated side. In other words, the reason I say it's less complicated, it has less pieces. Okay, so I have less options to work with. So, for example, it's not obvious for me what to do here. The only thing that's left is this. I don't have a lot of options. Gosh, the only thing I can see is maybe doing this, right? Well, I know 1 is equal to what when we talk about trig? I know it's equal to sine squared plus cosine squared. And of course, I still have this, the minus 2 cosine squared theta. Okay. All right. Oh. Well, that's cosine squared. That's minus 2 of them. So that's like 1 cosine squared minus 2 cosine squareds. Well, it's like saying 1x minus 2x. Well, 1x minus 2x would be negative x, right? Or in other words, 1 cosine squared minus 2 cosine squareds would be equal to minus 1 cosine squared. Okay, so sine squared minus cosine squared. All right, now what? Well, see, this is where sometimes you got to pull some algebra and you got to be a little inspired. But like, here's an example. This is an algebra identity. Okay, we'll do this in blue over here. If you have two squares that are subtracted, you should have this memorized. Comes up often. Excuse me. That is equal to a minus b times a plus b. This happens all the time when we're dealing with quadratics, right? Like I might have x squared minus 9. 9 is the same as 3 squared. So then I know that this is equal to what? X minus 3 times x plus 3, right? We use that when we're dealing with quadratics a lot, or we're trying to factor with polynomials, yeah? So this is like a trig, not a trig, this is like an algebra identity, okay? And so same idea over here. Oh, okay, so sine squared minus cosine squared, well, the a is like sine, right? Sine theta squared. The b is like cosine theta squared. So in other words, I can rewrite this as what? Sine theta minus cosine theta times sine theta plus cosine theta. Oh, look at that. Ta-da! That's what's on the left. So I've taken the right-hand side, I've manipulated it with algebra, and I've proven that I get what's on the left-hand side. So in other words, I've proven this identity is true. Okay? All right. And I actually used an algebra identity, essentially, to prove this trig identity. All right. Is there another way we could do it? Oh, I bet there is another way. All right. Let's take this side again, the right-hand side. I do like my cosines and sine squareds, and I notice, hey, you know what? Cosine squared could be rewritten as what? So this is 1 minus 2 times cosine squared. But cosine squared could be rewritten as 1 minus sine squared. Clean that up. Right, going back to that, sine squared plus cosine squared equals 1. So if I move the sign over, right, so cosine squared, I could replace that with this. Okay? All right. I'm going to distribute the 2. 1. Negative 2 times 1 is negative 2. Negative 2 times negative sine squared, that is plus sine squared theta. All right. Let me see here. That's not really doing anything for me, right? Okay. Because I'm like getting into this cyclical kind of situation, because now I'm back to sine squared. I got a 1, well, 1 and minus 2. I guess I could work with that. 1 minus 2 is what? Negative 1. Yeah, I mean, so I don't know. And see, and so this is where you can get into traps where you're kind of cycling back. This looks a lot like I have above, and so then what could I do? Well, I could take sine squared, and I could replace it with what? 1 minus cosine squared. But then I'm going to cycle back. If I replace this with 1 minus cosine squared, I'm going to cycle back, and I'm going to end up with what I had there. And so I kind of intentionally did this. But if you're trying to solve a trig identity, sometimes you'll do this. Well, you'll sub something in, you do a little work, and then you get to a spot. The next thing you try to sub in, well, it ends up looping you back to where you started. So what's that tell you? That tells you this isn't a good approach. It's not that you did anything wrong. It's just that I'm stuck. I'm looping, right? No. All right. So what that means is you should stop and maybe try the other side, right? Or try something different at the beginning. So start over with the right-hand side and try a different thing, right? So like on the previous slide, we swapped out the 1, right, for sine squared plus cosine squared, right? By the way, I could do that at this point, and that actually might get me there and help me get this figured out. But this happens sometimes. You get these loops, you get these things, you get sort of stuck. So stop, start over, pick the other side, maybe play with that, okay? So that's another piece of advice for you, and that can happen, right? That even happens to me. So there you go. All right. Let's see here. Let's look at one here. So here's a good one. So one piece of advice, and we did employ that here. We swapped out and looked for cosine squareds and sine squareds, and so I did that. And I think I even used, I used kind of that same cosine squared, sine squared thing back on this one. So now here's one where I like to get everything into sines and cosines, and that can really be helpful too, okay? So for sure, you're going to want to work on the left-hand side because there's so many things I could do with 1. That I just don't even know. I mean, of course, the obvious would be replace it with sine squared and cosine squared, but where do I go from there? That's kind of tough. So again, I think it's really helpful to work with the more complicated side, which I think is this side. And so that's what I'm going to work with. And the first thing I'm going to do is I'm actually just going to replace all these things with sines and cosines. So for example, secant squared is the same thing as 1 over cosine squared. Sine squared, I'll leave that. That's already a sine. Times, another secant squared. Well, that's 1 over cosine squared. Again, I'm trying to show, is that actually equal? All right. Oh. Well, this could really be thought as one fraction. And hey, look at that. I have a common denominator. And so, let's see here. I could just put these together. So this is all over cosine squared x, and then I have 1 minus sine squared times 1. Well, that's actually just what? That's 1 minus sine squared. Well, hey, I know that 1 minus sine squared is really just what? Cosine squared. And cosine squared over cosine squared is 1. Ta-da! So I've just proven this identity. So if I see that thing on the left, I could just swap it out with 1. Okay? All right, so that's nice. All right, let's try this one a different way. The other different way is I notice immediately, right? Again, working on the left because the left is definitely more complicated. So I'm going to, again, work on my left-hand side. And I do notice that both of these have a secant squared. So I'm just going to do some algebra. And if I factor out secant squared, I get what? Well, if I factor it out of this, I just get 1. And then if I factor it out of this chunk, well, it takes this one out, so then I'm just left with the minus sine squared. Well, hey, again, what is 1 minus sine squared? That is cosine squared. And remember, what is secant squared? Secant squared is really the reciprocal of cosine squared, or in other words, it's the same thing as 1 over... now, notice I said reciprocal. It's not the inverse. It's the reciprocal. There's a difference. All right. Oh, and again, boom, boom. Almost the same thing I did on the previous one, just slightly different. And there you go, that's equal to 1. And I got it. Okay. All right. So again, my tips, start with one side, work only with one side. See if you can get the other. Only swap out or look for sine squareds and cosine squareds. You can swap and do some things with those typically. Maybe change everything into sines and cosines, right? So all those are good tips. So those are my hints, if you will. And again, I love these. I think they're just like fun puzzles. But if your algebra skills maybe are your weaker assets here, these can be kind of tough, right? So having good algebra is a key to this for sure. And so maybe you got to brush up on those skills or whatever. But these are super helpful. Again, you don't really see these in isolation like this. Again, like this green chunk here might actually be part of a larger calculus equation. And I know that maybe if I pull this green chunk out, I manipulate it a little bit, or maybe I even remember this specific identity. Oh, well, now I can swap this green chunk out. That's really just equal to 1, and all of a sudden my larger calculus equation's easier. So again, this is really applicable. We might not get a lot of applications with it now, a lot of uses with it now, but it's a skill that we practice so that those of us going on to calculus, we're prepared to do that when we need to do it in calculus. Okay, because they're not going to really teach you identities in calculus. They're going to expect that you can kind of pull these out of your hat. All right. So that's the idea. I hope that helps with identities and proving identities, and I hope that just makes this section a little easier for you.